I'm not representing the views of any institution or organization. I'm just me. Okay. So the sort of the history of motivation here is, at a previous Fermilab philosophical meeting, we had Al Brunstein come and present ideas from his book, God and Randomness, where he ended by saying that the crisis in cosmology gave him reason to say it was more probable than not that God exists and created the universe. And that prompted me to think, well, what do cosmologists actually say about a crisis in cosmology? Because I hadn't realized there was a crisis in cosmology. So I went off and I checked a couple books out of the library: The Big Picture by Sean Carroll, The Singular Universe and the Reality of Time by Lee Smolin. And reading through those, Carroll promotes the idea of multiverse. And so multiverse I'm going to pop up several times through this talk. And Smolin investigates the concept that there's really only one universe, but that the constants of nature and all the rest of that can change over time. And we'll get a little bit into all of that. And so what was the crisis in cosmology that Al seemed to be referring to? So the astrophysical measurements are actually pretty broadly consistent, and there's very good information back to sort of 1 second after the Big Bang, and there's even fairly good agreement for a decent period before that. And then what he's talking about, though, is the fine-tuning problem. So our physics models, we say, connect two things by maybe the speed of light, and the speed of light is just a measurement we make, and so we have this arbitrary constant. Other type constants are the masses of the different particles that we find in the standard model and the strength of the various interactions. So we have all of these constants in there that we don't have a basis for saying what they are. Now, one of the steps in the history of physics was finding a constant for magnetism and a constant for electricity and a constant for the speed of light, and then suddenly one of them went away because those three are related in a way that you eliminate one of those three constants. So theory might be able to pull this together and get us to a smaller number of constants. But the point is, if those constants were different by even small amounts, the world would not work in a way where we could exist. So the question is, does that imply that a God decided on the numbers for those parameters and set them exactly what they needed to be for life? And I'm a physicist. I approach physics problems, figure out the numerator and denominator, calculate probability, and you're done. And no, it doesn't work that easily. So I was gonna, when I first was thinking about doing this, just go through a presentation on the information that's in The Big Bang, The Big Picture by Sean Carroll, where he tackles this small question on the origins of life, meaning, and the universe itself. So he's, really goes out there. It's a great book, but Sean, you can actually hear him give an hour talk on YouTube, and he does a much better job of it than I do, so you should listen to him. Okay, should I skip this? Anyway, so here we are in this philosophy club, and so because Alexei likes quotes, I quote Albert Einstein: "A knowledge of the historic and philosophical background gives that kind of independence from prejudices of his generation, from which most scientists are suffering. Independence created by philosophical insight is the mark of distinction between a mere artisan or a specialist and a real seeker after truth." And I'm sure I don't even rank as an artisan on Albert Einstein's scale, but it gives us motivation to look at the philosophy behind this. And then I included a quote by an actual philosopher about philosophy, that Aristotle maintained that women have fewer teeth than men. Although he was twice married, it never occurred to him to verify the statement by examining his wives' mouths. So I think that tells us that we should look to experiment as well as philosophy. So I started out, trying to put this in a philosophical framework, and I spent some time on epistemology, and I don't have time. But I am going to note that there's a saying, this is a version of it: if what you have is a hammer every problem looks like a nail, and I'm a physicist, and so you're gonna see that, and I cut out the rest of the philosophy. But some of you are physicists, some of you know more about this stuff than I do, but some of you probably haven't seen any of this, and so I'm going to try to label some of it as, you know, conventional physics, lots of experimental support, physics motivated, meaning that we have a reason to go to that theory, but we don't have the physics confirmation or disconfirmation, and then just so stories, which are sort of anecdotes. And so here's some basis just to try to get on board. That's my just so stories back of this, and that is physicists build models of the world using mathematics as a tool set. The math is very important, but some variable in that math you have to relate to some real thing you see in the world. And so physicists, you know, take all the math, relate that all together, and then try to make predictions, etc. And math does not tell you how the real world works. You have to do that with experiment, and you then use the mathematics to tie all the experiments together to get your model of the world. Further, the map is not the territory. The map is not the real math is not the real world. Although we've heard views that, in fact, maybe math is the real world. But this is me coming in, and I wanted to note that there are many, many mathematical models that you can make of the world that do not describe the real world. They just don't agree with experiment. And so another obvious thing coming in is that we can often mix up words, get them tangled in our minds. So in social law, the mind makes the law, legislator, and then tries to enforce it through judges. In physics law, what we're doing is we take a recognized pattern that's out in the natural world, and we say we describe that pattern. And what are called laws of nature, most of what you've heard as laws of nature, are approximations that are good over some parameter range. So there's some map. And I'm just going to use the word models as I go forward. So to part of this, I'm going to try to tell you some stuff about cosmology, because some of you probably haven't heard this, and some of it's really fun. But to go there, we have to understand the basis of where we are in physics today. So general relativity is our model of space and time. That's the stage. And, you know, we talk about various things. So this is my model of the universe. And it's expanding, okay? And what's expanding is, here the rubber represents space, vacuum, okay? So the vacuum, the space is getting bigger and bigger. And so that's our inflating universe in general relativity. And so to even start, you have to accept things like space expands, space is curved, parallel lines can start out parallel and then they're curving through the space and they can intersect. Twins can be different ages. We discussed that a few months ago and how Bergson kind of tripped over that. So I'm going to say a few things later. This is just to say these are the three things we have to worry about. The second thing is, in that space there's a whole bunch of particles, and that's what we do here at Fermilab. We take particles apart and go to higher energies and deeper, smaller distance in particles. We'll have a slide on that. And then at quantum mechanics, once you have the particles in the space, you have to say, I know what it is now, what's it going to be in the future? How do I predict how things move? And that's quantum mechanics, okay? And we're going to jump, and just because we don't have time to discuss any of this, some people in the past have said that the Big Bang is the absolute start of the universe, and maybe, we don't know. Other people talk about the Big Bang as some continuing process, so we'll say one slide about eternal inflation, cyclic universes. And the answer is we just can't go back that far right now with real knowledge. One other interesting statement is just that since gravity has negative energy, you can actually create an entire universe without violating conservation of energy, okay? And I'm going to skip the thermodynamics. So first of all, let's address general relativity, and I realize most of you probably don't work every day with relativity. I happen to, but and it may seem pretty academic, so I wanted to touch base somehow. And so I'm going to point out that one of the things that general relativity says is that clocks run slower in stronger gravity. Not just clocks, any physical process runs slower in stronger gravity. And so the GPS system that's right in, that this receives and tells me where I am so I can make it to my doctor's appointment, figures out where I am to a few feet consistently. And everybody else is using that technology pretty often. If you dig into that, the GPS system, if you don't do the general relativity correction for this gravity effect, your phone would drift by 6 miles per day, general relativity due to the gravity. There's also a smaller correction due to the special relativity due to speed. We won't go there. So you're using general relativity in your technology every day right now, okay? Just try to get some confidence building there. It's not okay and fun. So now we'll go to what we do here at Fermilab. This is the standard particle zoo. So what's over here is the quarks and muons, electrons, and neutrinos that we're studying at Fermilab. The right-hand side is all of the force carriers and how the forces map onto the different particles, etc. And so one important thing here actually is that all of these particles, we call them particles, and at various levels we work with them as particles. But the best theories we have to do the most precise calculations all say that those are actually waves, and we're seeing this little localized wave, and because those waves are quantized, we see them as particles, okay? From those particles that are really waves, you do calculations with quarks and gluons that you put together to get a nucleon, protons and neutrons to get a nucleus, like an oxygen nucleus, which is charged. Nucleus plus electrons gives you atoms, like an oxygen atom, which is neutral. Atoms join together to give you molecules, so an oxygen plus 2 hydrogen make a water molecule, everybody knows that. And then finally the molecules can lock together to make tables and everything else. So physics over time has gradually gone deeper and deeper into this. What I think is interesting is the Big Bang starts as a very high energy dense system, and it actually in its history goes just right down this list, okay? That's how things appear out of the Big Bang. And so that's why it was worth spending 2 minutes on that. Next, let's talk about quantum mechanics. There are several other models. So we can do the calculations with this quantum mechanics, but what's really going on under the hood, actually, we don't know, okay? So here are 2 models, one of which we've kind of discovered that consensus on that model sort of was around 1927, the Sauvé conference. And we've talked about Einstein and Bohr and some of their. So Einstein really didn't like this. He didn't think it was a complete theory, but this is what you find in the textbooks today, is that the world, there's actually this complex number that exists at every point in space. And if you want to say, here's an electron, it gives you this wave function that's underneath it, and then you have to square that in order to say what's the probability of that electron being at any point, okay? And then when you want to say how is that electron going to move, you apply the Schrodinger equation, and that tells you how it changes over time, okay? And they both agree on that. And then the wave function has superposition, and this means that if I want to take 2 electrons, I don't get to just put 2 probabilities there. I have to put this underlying wave function there with its complex numbers. And when I calculate this thing with 2 electrons, those complex numbers can cancel at some locations and add at other locations. I have to do all that interference And then once I've done all the interference, I square it to see probability of something actually happening. And both of these do exactly that. And LEDs, laser pointers, tunnel junctions, there's a lot of our technology that just relies on all these calculations work. So this is maybe even closer to us than general relativity. But when you look under the hood, here, when you do a measurement, Copenhagen model of how this happens is that you find that electron in one particular position, and that wave function you use to calculate it just collapses over the entire universe. It's gone, however big it is. And you start over with a new wave function that says, well, I saw the electron here. And where you saw that electron is totally random. It's not like throwing dice where theoretically you could tell where each die was tumbling and you would be able to predict it. It is random. The probability is totally deterministic, but individual electron measurements are random. And then you say, well, suppose has everybody heard of Schrodinger's cat experiment, or do I need to?
The poor cat.
The poor cat. You connect one atom and you say if it decays, I kill the cat, and if it doesn't decay in that half-life, the cat is alive. So this is Schrodinger, who was working on quantum mechanics. And so at the end of this measurement problem, the cat is either dead or alive. What Multiworlds does, Hugh Everett invented this in 1957, says, the wave function is there, and then you interact with that electron. Well, you actually are just made up of all these quantum systems. You're not something special. And so as you interact with that, you and that electron get entangled. And then as that wave function decoheres, is the technical word for it, but as that wave function continues on, part of you is entangled with the electron seen here, and part of you is entangled with the electron seen there. So what a measurement is part of you is entangled with the result of that measurement. And that's why it's called multiworlds, is because it's saying the cat is both dead and alive, and there's different versions of you entangled with each cat. Okay? And this wave function, it's totally deterministic. Schrodinger's cat is both dead and alive. Versions of you are entangled with each. It has some other interesting things that over in this version, wave function functions as an arrow of time. It collapses, it never uncollapses. Okay? Whereas here, since you didn't collapse the wave function, Schrodinger's equation is time symmetric, just the same way it is in Newton's, and it has the potential to be less spooky. Remember Einstein talked about quantum mechanics as spooky action as a distance. So let's move on to actual cosmology. And so here's my analogy to cosmology, is that you are all familiar with, there's a bunch of water molecules up in a gas in the air up there. And as you cool down the temperature, those molecules tend to kind of stick together loosely, and they're moving around as water. And then you get the temperature low enough and they freeze out in some pattern and they lock. Okay? So these are actual natural snowflakes that some guy actually very carefully took pictures of in a microscope. And you see that this system up here at the top at high temperature is a very simple system. It's just a gas. And as you lower the temperature, you went through two phase transitions. And at the end, you froze out this fantastic pattern of all different kinds of things at the end. It's really fantastic. So we're going to use that analogy in looking at cosmology a couple times here. This is there a way to get rid of that little box?
Got it.
Got it. Okay, got it.
Yep.
So this is the timeline in seconds, and I kind of apologize. There's 1 second, and this is scientific notation, but rewritten in computer e's. So E means 10 to some power. And in that, our universe is about a little less than 10 to the 18th seconds long, 13.8 billion years. And as we go back every little tick mark means a factor of 1,000. So you can think of going from tick mark to tick mark is order of magnitude like seconds to hours. Unfortunately, our time is not metric, but and then you go back to really tiny instants, and we know our theory of general relativity doesn't work here because general relativity, is not quantized. The gravity itself is not quantized. We know our theory does not work here. We can't extend it back there. And that's the main thing that sort of, without that, we're not able to say, did the universe just appear, or how did this really happen here? But we can work backwards at varying levels of confidence, and I will note that there are some density fluctuations very early in the universe. This is a hypothetical time when the universe is expanding, but all of a sudden it really went into overdrive, and it just spread stuff out fantastically. It's called inflation. Then eventually it cools down to where we just have the quarks. Eventually it's cool enough and far enough apart that those quarks can settle down into neutrons and protons. Those neutrons and protons can stick together into nuclei, hydrogen, helium, tiny amount of lithium. Eventually they cool down enough that the electrons can stick and form neutral atoms, and that happens here. And then there's those atoms clumped together, we get stars and galaxies, and we get to us.
Could you show where Higgs boson and top quark are?
So they're around here.
No, much to the left. 45 orders of magnitude in total, 45 orders of magnitude. So
Yeah,
it's 10 to
but-
the minus 29.
But we produce Higgs bosons here. Okay, this below this energy is where Higgs bosons freeze out.
Really? I think it should be more to the left, but okay, let's go.
Okay. So there's the hypothetical particles, the inflatons are way back here, and they freeze out around here. And then you're mostly radiation dominated, is my belief, through this period. And the Higgs field is important through that time. But yes, Higgs bosons can be around during that time. But at sort of this point, you don't see individual Higgs bosons. It's when they freeze out, but our accelerators get back that far. Okay, so but that's not okay. How come this doesn't? Okay, why isn't it moving?
You got rid of that thing at the top.
Because you got it, yes.
Oh, I got it. How do I unget it?
Look up there and do something.
Oh, okay. Good with the equations and bad with this. Anybody know how to ungot it?
That's really, we were just joking about that.
Yeah, okay.
Stop the arrows and the turn and the mouse clicks all go move. On the right click.
There we go.
Okay, here you go.
Something, yeah.
Oh, something happened, but I got to get rid of my window.
Ah.
No.
Keep push no.
Look outside of that box.
Okay. Click. I can't get back. Okay, I need
Just
to.
minimize it.
I don't see a
No.
minimize thing.
Yeah, click on.
Oh, okay, we're there. And now let's see if I can't navigate. No, I can't navigate. Oh, this is ridiculous. Okay. Stop sharing.
And then you have to connect again. 2951.
Dang. Okay, I've got it on my desktop,
Oh, it is there.
and I'm back. And I have control again. Okay, that's nice. Okay, so because we better know what's near in time to us, and besides I can show pictures, I thought I'm going to start actually from now. And so it's kind of interesting to me. The other day, my son came up and said he was chatting online with flat earthers. And so yes, the Flat Earth Society still exists, in spite of the fact that we actually have now a weather satellite that you can take frames and stitch them together, and you can actually see the round Earth going around. So everybody, I'm assuming, here's our Earth, there's where we live, and our Earth is ellipsing around our sun, and there are many other suns out there, and we actually can see the planets around the nearer one. There's like over 4,000 planets seen so far, and we're just going to start there and we're going to move out. So the interesting thing in cosmology about planets is that the elements that make up that planets actually come from stellar explosions. So out of the Big Bang, there's only really hydrogen, helium, and a little lithium. The rest of the elements are created in star burning and stellar explosions. And different elements come in each of these different kinds of things. So in particular, oxygen is created in those stars and is available for planets only after those stars explode. And here's a picture of a real explosion. And then we can move out, and now we're to the scale of galaxies. And since I'm talking about multiverses, which seem, how can the universe be that big? I'm going to start with just saying, well, even the universe we can see is pretty darn big. So we don't have a picture of our galaxy because we don't have a satellite outside of it, but it seems like it's pretty similar to this one. This is the closest big galaxy. It's the Andromeda Galaxy, and it's 2.5 million light years away from us. It's headed towards us and will merge with the Milky Way, with our galaxy, about 4.5 billion years from now. And it's not going to kill us, but it's, well, I won't be alive by then anyway. But anyway, 10 to the 11th, and this galaxy is probably more like 10 to the 12th suns in that galaxy. That is a lot of suns, and we know most of them have planets. So that was an example of one that's really close so you can see it. This is no longer a picture. Fermilab worked on this thing called the Sloan Digital Sky Survey with a telescope, supported that because there's a lot of data in this stuff. And so this is a plot of galaxies, a 2D slice through a 3D knowledge that goes from where we are out to 2 billion light years away from us. And no, it doesn't mean that there's no galaxies here, that's just not mapped. And out here there are galaxies, just not mapped yet in this 3D manner. So this is kind of amazing. There's a lot of knowledge that you can derive, like the number of neutrino generations, from this overall pattern and its correlations, but I don't have time for any of that. Okay, so then how many galaxies are there? 10 to the 11th stars in a galaxy. Well, this is the Hubble Deep Space. They just pointed the Hubble, the best telescope we have, and let it point at a certain tiny small region of sky for as long as they could. And almost every dot on this picture is a galaxy. Okay, and this reaches back almost. So to really see the 13 billion years away from us stuff, you have to use some tricks like gravitational lensing. But these galaxies really just extend out and out and out, okay? And so if you multiply the number of galaxies by the number of stars in the galaxy, you get more than 10 to the 22 suns in our visible universe. And we'll get to visible in another couple slides. So if you think about it, though, you're looking back 13 billion years. The universe is only supposed to be 13.8 billion years ago. Where is that big explosion? Shouldn't you be able to see bright light from that explosion? And in fact, that bright light is reaching us. It's just invisible. So how can it be invisible? Okay, so this is, you point a microwave detector that can detect frequencies lower than our human eye can see. And you point it at one small part of the sky, and you can get the spectrum as a function of its frequency. And then you can point it at every single dot on this map that's an expanded sky map, and you can get a spectrum like this everywhere on each of those pixels. And that's the picture of the light coming to us from the Big Bang from all around us. And it only, you have to take that picture and then you have to turn the contrast way, way up, because the variations across this are only hundredths of a percent, okay, difference in temperatures. And then what physicists do, cosmologists, they take that map and they say, I'm going to look at the correlation between all of these temperature bumps. And this is it expanded sort of in the same way as a Fourier transform, but it's a multipole. And it has various bumps, and each of those bumps depends on speed of light, Hubble speed, how many neutrino generations there are, all sorts of stuff. And so there's people that spend their lives modeling how the theory goes through each of these bumps and what you can get from each one. And why is it in the microwave? I don't know if this will work. So there's a little wave here, photon. And as the space expands, that photon gets spread out. Higher wavelength means lower frequency. And this light that started out at about 3,000 degrees, and it really doesn't matter whether you think centigrade or Kelvin or even Fahrenheit, is really hot. And yes, if you were there, when it happened, it would be very bright. But that's expanded over the time of the universe. So this light is now 2.7 Kelvin. It's 2.7 degrees above absolute zero. So it's really, really a cold universe now. And I am okay. So if that happened here, the light couldn't escape before then because there's too many charged particles and the light is just bouncing off charged particles. So this is where we get atoms. Electrons get down and they stick to the nucleus, and so you have neutral things, and the light can stream out to us from this point, from 380,000 years after the Big Bang. There's another pretty solid calculation that we can check, and that is the ratio of different elements that were produced in the Big Bang, which is hydrogen to helium to lithium, and that's what this was about. So this is, we do experiments on Earth, and as a function of sort of how dense things really were, we can run the theory and say if we started just with this really high temperature protons and neutrons, and we cool it down and we cool it down and expand it as the universe expands, this is how much helium we should see. This is how much deuterium we should see. Here's helium-3. Helium-3 turns out it's hard to see. This is how much lithium we should see as a function of this density. And then we had that cosmic microwave background, which tells us basically what that ratio is, what the density of particles were. And so when we look for these different elements, we should be looking where those two lines cross. And this yellow box here says this is where helium should have come out to the best we're able to measure it. There's a little yellow box here that you can't even see back there, right where these deuterium and the CMB cross, that says that's where deuterium should have come out. And this says where lithium came out, and you might think, oh my gosh, you missed the box. Yeah, and you missed the box by a factor of a couple, 2, 3. But you have to realize that this is a calculation that's telling you how much lithium-7 there is compared to hydrogen at the level of 1 part in a billion or 1/10 of a part per billion. I mean, the fact that you can calculate that nuclear reaction to 1 part in 10 billion is already pretty impressive. And yeah, there's probably some modest physics or observational error we have there, but it's pretty good evidence. So we have, back to this time, and this is why I say we have to produce oxygen when stars explode. There are actually measurements of all these things from early in the universe, and it's way too complicated to go through in the few minutes I have. But this gives us a pretty good data point, and our accelerator interactions, we can get up to the similar energies and the similar physics of about here, and then all of this we have to extrapolate to, although some of these density fluctuations leave some footprints in the cosmic microwave background. Okay, so our analogy is that we started with this quark-gluon plasma that then froze out into stars and eventually planets and everything else as temperature went down and things froze out. So here I'm getting to something that I think is actually very interesting and people may or may not have thought about before. So this is a complicated drawing that I stole from the web that allows you to relate on this plot what happens as the universe expands in space and over time, and how light travels and all sorts of good stuff. And the idea is we're on this vertical line here as a function of time. Gigayear is 10 to the 9th years. We're here at 13.8 gigayears right now. And this is 10 million years after the Big Bang here, so I guess, I don't know. Anyway, and then we're running the timeline sort of logarithmically off towards infinity. And this, we're fighting the idea that as the universe is expanding, if you produce some light here and you want to get to you here, that light is moving at some speed. And if the universe is expanding faster than the light's moving, that light's never going to get to you. Everybody understand that? Okay. So the light has a finite lifetime, and so this scale is not constant. This is how far something is from us right now on this line in terms of giga light years, billions of light years away. And so what can we say from this? We can say, well, suppose a galaxy formed 100 million years after the Big Bang, and it was 30-some billion light years away from us now. Back then, it was a factor of 20-something closer to us. It emitted light then. That light is getting to us along the light cone right now. Okay, so we can see what happened there that many billion years ago, not very far after the Big Bang. As we go time forward, eventually, I mean, we will be able to see what happens to that galaxy until what happened about 5 billion years ago, or no, not 5, 13.8 minus 5, 8 billion years ago. And then it's going to be moving away from us so far that light from it will never get to us again. Okay? So it's receding out of our view. And if you look at this infinity point here, it says we will be able to see things that we're up to about a little over 60 billion light years from now. We've already seen most of the universe that we're ever going to see because we can see out to 40-some billion light years now, and we'll be able to see out to 60 billion light years. And then there's also stuff out here that we never saw light from and we're never going to see light from, okay? And so the question is, an interesting thing is, how much stuff is out there that we never are going to be able to see? So this is an analogy to flatness of the observable universe. Is thousands of years ago, people could get an estimate of the size of the Earth by having a stick, and this is all out of proportion. You need like a couple hundred miles between these sticks. But you can see that there wasn't any shadow on this stick. This stick had a shadow, and you do some geometry and you get the diameter of the Earth. Okay? So in cosmology, it works a little bit different than that, but similar concept. And we now have measurements of the flatness of the observable universe. And so we know we can see out this far. The question is how much more of it is out there. And currently the maximum deviation from flatness, okay. So here's a flat universe, and it just extends everywhere, right? And a triangle, 3 triangle angles is 180 degrees. If I still had my balloon, I would be able to show you that the sum of the triangle here, there's one side, you have a right angle here, there's another side, you have another right angle there, there's another side, you have another right angle, 270 degrees on that particular triangle. So how well does the geometry line up gives you an idea of the size of the thing. And this is now measured to like 0.25% flatness. And so the universe is actually several hundred times bigger, at least, than what's observable, okay? So the volume of the unobservable universe that's beyond light ever got to us is at least 100 times in radius, which means 1,000,000 times in volume. And so it means that if it's all like us, it's at least 10 to the 28th suns out there in all those galaxies, right? Well, now we're sort of on the edge of physics and into metaphysics, possibly. So the observed flatness of the universe says there's an unobservable universe as well as an observable universe that's so big that, in fact, many parts of the unobservable universe are unobservable from other parts of the unobservable universe. There's at least millions of mutually unobservable universes, although they're all connected on the edges. And they don't interact with us. The light will never get to us. We'll never see them. So are we scientifically able to talk about them? So my claim is this is, it's yeah, okay, fine. We have the estimate. I think we're allowed to talk about them. This is our first sort of example of a multiverse. But it also says there are limits to just what we're ever going to know or see. Okay?
See, that multiverse, that's still one universe that they're talking about there, right?
It depends how you want to define. Yes, I mean it depends how you want to define universe. And if you define universe as everything there is or can ever be, then all the other things, like the quantum mechanical separation into multiworlds, is still a universe, but people tend to call it a multiverse. Okay, and so if you're never going to be able to have contact with it, okay. So let's go on, and we can certainly come back. So there's 4 different kinds of multiverse that I'm going to get here there, and this is the one that's it's most closely to just saying it's universe. Might be infinite, might be millions of times bigger than what we can see. So the next concept is this inflation model that space expanded very rapidly during one period of time, and much faster and much faster is a vast understatement. It really inflated hugely fast. So inflation models were invented to explain several features of the Big Bang. It wasn't really, I want a multiverse. It's that there are quantum fluctuations you see in that CMB radiation and in the structure of galaxies. And inflation can tell you how little quantum fluctuations, like my wave here, expanded to be the size of the things we see. It allows different patches of the sky to have communicated with each other early in the universe, so you understand why the temperature distribution is only 1/100% across that sky. There's some other theoretical stuff that I'm not deep into, like not seeing monopoles and other relics from the Big Bang. So you start that, you develop this theory that's a little bit like the Higgs theory in that you say, okay, there's another particle called the inflaton, and you have anyway, the end part of this is that once you start that inflation, the sort of natural way the theory wants to go is that different parts of it can inflate at different rates. And one part of it is our bubble, our local universe, and other parts of it keep just zoom, inflating and spinning off other little bubbles. And you get to this kind of multiverse, which says you have all these bubbles that are very disconnected, that are disconnecting way back when. So there are different, you can think of them as other universes, or you can say everything's the universe, and you say these are other sub-universes.
And there's really no evidence for a bubble, an actual bubble. This is theory.
So this is theory, and so we don't have confirmation of this. But what we have is we have some reasons to postulate the theory, and there are possibility of observables. So some people claim that if we can observe B modes in the cosmic microwave background, which was actually claimed a couple of years ago, and then it's thought, well, okay, there's too much dust in background to claim that. But B modes would have, okay, they interact with this, and let's ignore that for now and talk about that.
Disputable. This theory is
This theory is absolutely disputable. Okay, so inflation is absolutely disputable.
contrary to other theories which you mentioned, like general
Yes,
relativity.
yeah, and so I
quantum
tried to.
well established.
I didn't make the boundary. The stuff up that I was putting in green is stuff that we really have data, and we really have mileposts. And in fact, I put up in the corner, I didn't mention it, that yes, most of the others were physics conventional theory. This one I've labeled physics motivated. Here are the motivations which aren't there from saying, oh, I want a multiverse. But you do that, and you end up with a theory that can easily be a multiverse. That's, I think, the right way to say for it. And string theory is like that as well. So decades ago, I would go to presentations by theorists, and they say, oh, we're going to build this guts theory. We're going to have M theory. We're going to have everything fit together in one unified theory of everything. And it's going to explain why the constants have to be this to each other. And so they're building this theory. And then string theory came along, which is based on vibrations of extended objects. So before we were looking at particles where we said it's a point particle and you go to singularities that produce infinities. And string theory gets rid of infinities by saying, you know, an electron is actually a string, or a vibration of a string. So this, I think, drove the early, I mean, I'm not a string theorist, but it's ideas like this which drove people to look into this, and then people really got excited because in the other theories they have, there wasn't any way to quantize gravity. That's been a problem for a long, long time, okay? You just didn't see the graviton there. And string theory contains in its mathematics things that can allow you to have gravitons and go in and do the quantum gravity theory, okay? This also, it has physics motivation, and eventually we might actually experimentally test it, but yes, right now it's physics motivated, and it's a nice theory, it's a beautiful theory. Well, I don't know, I don't go on beauty, but the consequence of this, when they were looking for this thing that would fix all the constants to a certain thing, is that they discovered that string theory can describe 10 to the 500 more than that number of different universes. And you can view this as a bug or a feature. And so it can have different numbers of dimensions, different particle structure, different constants. All of those things fall out as you take this high energy theory and bring it down to scale, and that's called the landscape. And so some theorists are horrified because they say this makes physics and environmental science. We can't predict which one of these universes we came down from. And others say, well, okay, you know, it describes the universe, okay? So there could be an infinite number of bubble universes of types where there's more than 10 to the 500 different types of universes that can be happening. And that's kind of mind-boggling. Anyway, this multiverse from string theory could easily produce us and solve this problem of us being in a certain range of phase space. The phase space may just be that big, and we just randomly get our constants. And there are people working on, for example, the Boltzmann objection to that, but I'm not going to go into that. So my going into this saying, I'm going to try to see whether there's a reasonable probability from a model that produces the world I have to end up saying we could be the result of string theory multiverse, okay, which has physics motivation in those theories, and that string theory could be freezing out into all sorts of different universes. Still, there could be some model we haven't developed yet that just freezes all the parameters and explains everything we see, okay? We don't know. It's beyond the edge of what we know. Could it be a special creation by God? Yes. So, not enough data yet, and possibly not enough data ever. And then, this is we're talking philosophy now, not physics. Finally. So what does this all have to do with philosophy? So Deism, in my naive understanding, is the assertion that a supreme being created the universe. So there's unmoved mover, first cause, cosmological fine-tuner in Al's statement. And so I'm just saying this is beyond the end of my knowledge, but I will note this is a time-worn argument that personally I find fairly strong, is the assertion that the most complicated, powerful, intelligent, supreme being was there from the beginning, from nothing, and started the universe, is a little counterintuitive to a physicist. If you look at that inertial complexity of a supreme being to the known evolution of the observable universe from a relatively simple state to greater and greater complexity, or you can look at the observed evolution of life from simple to more complex, or the initial complexity in the evolution of intelligence from rather unintelligent organisms up. It seems, so this is what gets into my intuition. This is a just so story, absolutely, I realize that. And so, deism is possible, fine. And we'll all disagree on it. I did one thing that's much more dangerous. Okay. I went and pulled out my Bible. Okay. And I wrote down the first chapter of Genesis in chronological order. So day 1, day 2, day 3, day 4. And this is not the inflation part. This isn't the string theory part. This is the part from the CMB, the part that we actually have good observations of and real data on. And I wrote down its order. And I'm taking my life in my hands here. The order does not match. Okay.
No one reads Genesis that way, if has any serious claim to be a theologian.
Wait a minute. Let Jim finish.
Okay, so for what it's worth, Genesis says stars are down here after water, earth, life. And here you saw that we had to have stars that would then, some of them burn up in order to produce oxygen so that we can have water and planets. And the order just does not match. And I realize people will have different, and I didn't quite make the hour, partly, but I'm going to blame my laptop problem there. I'm going to say that nature can be pretty amazing, and there's my understanding of the universe. And this is a picture I just like, which if you stumbled on it, a person could sort of lay down in that little circle. And this is a bunch of gravel circles that you find. And I can't pronounce where it is. And you look at that and you say, gee whiz, what kind of animal made that? Okay. And in fact, there's a paper written on this which goes through the whole physics way this happens. And this just happens due to thaw-freeze cycles. And the freeze-thaw cycle sorts out the different size pebbles, and you end up with this fantastic array of rings. And so that's sort of my vision of the universe right now. I thought I'd try to end on something fun. I don't know. Anyway, that's it, and I'm only 5 minutes over. Sorry.